This is the Secure5G4IoT demonstrator. The purpose of this demonstrator is to showcase two situations as follows. The first one applied to Work Package 21, which is assisted living and community care, in which a patient or an elderly people, for instance, is at home and need assistance after falling. The idea here is to detect this fall and then notify available caregivers that are at a reasonable proximity radius. The healthcare center will then open the door based on the caregiver eligibility. The second one is applied to Work Package 24, Building Block 24L, Adaptable Network Slicing, in which we showcase how can we apply network slices to specific domains, such as healthcare and smart home. To better comprehend the purpose of the demonstrator, we are now going to illustrate the following scenario. In our case, the smart home has a fall detection device, a smart lock attached to the door, and a gateway to connect the smart lock to the cellular network. A QR code is also fixed at the door to let the caregiver scan it. All caregivers and their apps are connected to the healthcare center through this slice. The healthcare center will take care of all validation requests with the help of the associated identity provider, which will verify not only its identity but also confirm its eligibility alongside with the platform as to interact with the premise. In a more detailed approach, what happens is, firstly, the fall detection device and all caregivers are connected to the healthcare center represented by the server component in this diagram. After a fall has been detected, the healthcare center will save the house ID to check later on the eligibility of the caregiver. Then the healthcare center will send an alert to all online caregivers. All online caregivers got an alarm and are free to accept or refuse the mission. When a mission is accepted, the healthcare center will notify all other caregivers that the alarm is now off. When the caregiver who accepted the mission reaches the house, he or she will have to scan the QR code displayed at the door. This will send the QR code info back to the healthcare center to check that the info matches the house ID and that the caregiver is the only one who previously accepted the mission. If everything's fine, the server will send the open command to the gateway app and the door will open. So this is how it works. A patient is at home and a fall has been detected. After the fall detection device has been triggered and issued an assistance request to the healthcare center, a dispatch will occur to all available caregivers that are connected to the dedicated network slice. Caregivers receive the alarm and can choose to accept the mission or not. When one accepts it, all other caregivers will be notified that the alarm is now off. Once the mission has been accepted, the caregiver will scan the QR code available at the patient's door. Then, a verification of the caregiver's identity and eligibility will occur, and after both situations are cleared, the healthcare center sends the open command to the gateway, which will open the lock. It has been mentioned that in order to verify a caregiver's eligibility, its identity must be checked in order to assert that he or she is able to accept the mission. However, how is it possible to do so? This is possible through the introduction of a new component in the network infrastructure called Identity Provider and Management System, which will be in charge of issuing and managing all identities linked to every device that is connected to the network. This will allow to allocate all caregivers' devices to the healthcare network slice. This new component is implemented by using an instance of the Glue server, which is an all-in-one identity provisioning and management tool. With the administrator profile, it is possible to control all verification attempts that have happened, as well as creating OpenID clients, the standardized protocol for identity provisioning to third-party clients. In order to reach a consensus on which parameters can be used as identifiers to create an identity, also known as federation, we need to establish a common ground between the network, in particular the home subscriber server, and the identity provider. To do so, we've created the Federation API that allows us to establish identities based on each device's SIM, such as the MC or the IMEI. With this, all registered devices in the network have now a nation identity ready to use and are managed in such a way that they can be deactivated and blacklisted in the case of an attack or exploit that has come for a certain device. As for the caregiver in our case, a companion app is also deployed in its device, which will mediate all verification requests, making it sure that he or she confirms its identity and thus being eligible to accept a mission. This is the 5G4IoT Lab early 5G network testbed, comprised of open-air interface instantiated software locally and in an OpenStack cloud. As represented in a picture, the Evolve packet core is deployed in the cloud and given on the left monitor, to which a baseband unit is connected, that is the PC on the right. The radio fronthead consists on the remote radio head instance, which is the small Intel PC in the middle, and hosts two eNodeB software-defined radio hardware USRP B210 boxes, each operating on band 3 1800 MHz and band 7 2600 MHz respectively. The eNodeBs exchange information via an X2 interface, which ensures soft or hard handover independence of the mobility of the user equipment device, that is the Huawei P10 Lite phone with a self-programmed SIM card. If we list the interfaces from the PC that runs the RRH, we can see that the machine belongs to the 192.168.10.0.24 network. The RRH is instantiated in a Docker container as well, and we can list the network to which the container is assigned to. We use the MAC VLAN driver for the purpose of setting the container to receive a MAC address and become part of the physical network underlay. In order to establish a link to the cloud core network, a tunnel has to be created that can interwork with the Open vSwitch from the OpenStack cloud infrastructure, and therefore a script is built that automates the deployment of OVS GRE tunnels. The script builds a GRE tunnel and assigns the Docker interface to it, allowing for remote connection to a cloud VM in which the EPC is running. The Evolve packet core is executed as represented in the figure on the right. As we can notice on the top left screen, the same MAC VLAN driver is used to run the containers with a MAC address and join them to the physical network. Now, if we enter the container and check the IP address, we can see it is part of the physical network with its own IP. For building the EPC, first the SQL database needs to be initialized and the necessary web servers up and running. Every component of the EPC is initialized using a script. Example is this script for starting the HSS. First step is now to run the HSS server, which has a configuration loaded from a file with operator keys and all necessary elements. At this point, the HSS will listen for incoming connections from a MME instance in order to perform diameter message exchange. A similar approach is used for initializing the SGW and the PGW by a script, which then assigns GTP interfaces by the SGI interface. The configuration of the same is initialized with the first script, which assigns interfaces in a configuration file pulled from the machine or container where it is residing at. Analogously, the MME is run with a script using configuration in a file that points towards the adequate HSS and SPGW. Therefore, the connection is registered in the HSS. Now, as the core network is running, the MME listens for incoming connections from the remote radio adds, i.e., baseband units. At this point, if we dive deeper in the configuration files, initially of the SPGW, the initialized interfaces of the container and the appropriate IP addresses are set, as well as the ones of the GTP tunnels. In the MME configuration file, we can observe the DNS realm, as well as mobile network codes, tracking area codes, and others. Also, the connection towards S11 interface must be specified and a GTP tunnel initialized as a sub-interface with separate IP. Similarly, the HSS is configured in a file to specify an operator code and the localhost IP address as a local server. Back at the radio fronthead, the configuration of the parameters needs to be precisely calculated in order to have a viable connection to the UE. The same TAC, MCC, and MNC need to be used for connecting to the MME. All the signal parameters need to be calculated in order to minimize interference from the commercial networks, band 7 in this case. Two times 2 MIMO is enabled with a 5 MHz wide channel, 110 dB RX-TX gain. Any higher values will require better CPU unit and more computational resources at the physical level. In our deployment, we have a scenario where a single baseband unit connects to a single MME. Each instance analogously has its own corresponding remote radio head. Running the radio fronthead is executed within the scope of the previously explained configuration file. An SCTP message exchange is registered between the MME and the radio fronthead. As the USRP drivers initialize, the radio transmission begins and the local available devices are expected to attach afterwards. Here, the registration of the base station can be observed as the MME responds with a successful SCTP connection. For establishing a precursor for the network slicing, the eNode B has to be split into baseband units and remote radio heads. The configuration of the baseband unit has to encompass an instance of each in the config file, pointing towards a specific MME. Similarly, the configuration of the remote radio head is specified in a config file. There, the radio unit numbers can be assigned, each corresponding to a single USRP B210 SDR hardware. This is an example of a configuration of the remote radio head. Each instance has to be specified in the config file pointing towards the corresponding MME as previously explained. As follows, the established network is listening for devices to attach and receive an IP address so they can connect to the Internet. The base station is running and registered to the core network. A UE mobile phone uses a self-programmed SIM card, and we select the corresponding APN with the same mobile country code and mobile network code. The phone attaches to the network, and there is a diameter authentication as shown on the left screen at the MME instance where it's being registered. To browse the Internet, the mobile data network has to be enabled. Notably, the phone is connected to the open air interface network and can play a YouTube video in high definition as an example.